Post is here.
Good morning, Post. Maybe you want to turn on all the lights. It might be easier to see your paper and stuff if all the lights are on. Oh, look at that. Bright and cheerful already. All right, well, I guess we'll get started. Couple quick things. The homework. I've had a couple people, or one person actually, email me with some issues with due dates. I'm going to, if you've had an issue, just make sure you email me so that I can take care of it. If it's something on my end, if it's something on your end, then you just need to be on task, as it were. The other thing has to do with post. I understand that there has been some disasterific happenings over there. But I noticed that you're logged in this room. Will you be able to be in this room on Thursday?
Yes.
Okay, then the test date has not changed and everything is still set to have our exam 1 on Thursday, and it will cover chapters 1 and 2. If you have any questions on the homework or the whatever, please continue to email me, and that way you can get your questions answered between what we cover today and the exam. You can get those questions answered as you study. The exam will consist of more than 10 problems, less than 20. I'm not quite finished writing it out. Your facilitators should have the exam in their email by tonight. Hopefully tonight, but worst case scenario by tomorrow morning. And that will be printed off. You'll be in here, and I'm going to try and figure out a solution for you to ask questions during the exam without interrupting any of the other students while they're taking their exam. So, and again, your facilitators will have those instructions if they exist, and that's how we will run the exam on Thursday. So, all that said, are there any questions on the homework?
I had one on 3 of my problems. My answers were correct, but it wouldn't give me the credit for it.
Do you have specific examples? Like which questions? Hello?
1 second.
Okay.
Number 5.
Number 5. Okay, so this is just a graphing problem. So let's switch over to the PC. Here's our graph. You can always and should always use the zoom in tool, and that will make the graph look bigger. And so we have 3 times x minus 5 squared. So real quick so we can list what's going on. So we have 3 times x minus 5 squared, and this is our function. And the things we want to know are the parent function, that's going to tell us the shape. The parent function will be x squared. And then the transformations in order are that we're going to shift to the right by 5. Common mistake is to shift to the left, and then we're going to vertically stretch by 3. Now, the shifting to the right by 5 is easy. We're just going to take the parabola and move it. But what we want to talk about here, or the thing that's going to be a little bit more interesting to graph, is that stretch by 3. So there's our x squared, and then we've moved to the right by 5. And now I need to know how to vertically stretch by 3. So this is the good time that you probably, at least for the graphing part, you probably want to look at a table. So we'll have x minus 5 squared, and then we'll have 3 times x minus 5 squared. And since x minus 5, since we shifted to the right by 5, I want my x values to be around 5. So say 3, 4, 5, 6, 7. So 3 minus 5 is negative 2, square it, we get 4. This will be a 1, and this will be a 0. This will be a 1 again, and this will be a 4 again. And now if I multiply by 3, we'll get 12, 3, 0, 3, 12. So far so good? So now let's go back. So what we're going to need is we're going to need a parabola, and there's a tool for that. There's a parabola button, but we're going to need 2 points. That's the first one because that's my vertex, right? That's my reference point. But then I'm going to need something else to put in there so that the graphing tool knows that it's the correct parabola. And I would go with either 4, 3 or 6, 3, because those are going to be the easiest to work with. So come over here, and right here we have the x squared tool. It's the second one down. So we click on that, and we're going to find 2 points. So the first one I'll find is my vertex at 5, 0. You should be able to see, it's a little faint, but as I move the mouse here, I have crosshatches, and if I look in the top right corner, there's a coordinate there. And I know you probably can't make out what the coordinates are, but it's the x and y coordinate that I'm homed in on right now. So I'm going to go to 5, 0. Oh, and see, this is just giving the interaction. So we're going to so it tells us actually, or we can tell it. So we're going to vertical stretch by a factor of 3, and we're going to horizontal shift by 5. there's our graph, and we can see that right here is 0, 5, like we wanted. And if I go to x equals 4, that's going to line up with y equals 3 right here. And we should, yeah. So, in this case, one of the things that you might want to do is graph on the calculator. I don't know what, I suppose I can look real quick, but then that'll take, well, it won't be real quick. Is this similar to what you already did? Like
Yes.
so let's do the wrong graph, just because. And we're going to, well, here, we'll just leave it all like that. Blah. And so, yeah, we get this whole thing going over all of the transforms. It doesn't give a picture. Okay, I'll have to look at those individually, but if you went through and you did something like this on your own paper, and it's still saying you're not correct, then that might be an issue. If you have your work on a separate sheet of paper, make sure that that's saved somewhere, because I might ask you to send it to me just to see what's going on between what you've submitted and what my math lab has graded. But yeah, if you were doing these things, you should have gotten the correct graph. The only other thing I can think of is that there was a typo of some kind in these 4 boxes, which is my math lab, that is possible. I'm sorry I can't be a little more help with that one. Any other questions from the homework? Everybody can transform like a transformer? Okay, then today we will finish up chapter 2, get ourselves ready for the exam. So we're going to talk about combinations of functions and inverse functions. That is the topic today. So recall we have a function and I can't spell, but that's okay. Alright, so we've got f of x equals some algebraic expression, right, or g of x is some algebraic expression. That's 3 times x minus 5 squared. Now, one of the reasons that we've covered functions the way we did is that functions are a fundamental unit of mathematics. So if we do some personal math history, first you said, hey, there's these things called numbers, and you would add, subtract, multiply, and divide. And then you said, hey, not everything subtracts to a positive number, that gave you negative numbers. You said, hey, everything doesn't divide evenly, that gave you fractions and decimals. You went on from there to talk about exponents and also nth roots. Then came pre-algebra and algebra 1 and 2. That was variables. And all that was numbers you don't know. But we can still add, subtract, multiply, divide, take powers, and take roots. I don't know what they are necessarily, but I know how to manipulate them in these ways. That's what we covered in Algebra 1 and 2. The next unit up from that is the function. We can add, and this is the point. We can add, subtract, etc. functions. And we do this to create other functions. So adding and subtracting functions is going to occur exactly the same way you think it does. If I ask for f of x plus g of x, we're just going to take each object, substitute it in, and then simplify the result. So let's say that f of x is equal to x squared minus 4, and that g of x is equal to 2x plus 1. Then for f of x, I'm now going to write x squared minus 4, and for g of x, I'm going to write 2x plus 1, and I will emphasize here, like I've emphasized all semester long so far, when you make these substitutions, use some kind of delimiter. Use parentheses or use square brackets, whatever's going to remind you that you have an independent object coming in right here, and you have an independent object coming in right here. This is what helps prevent sign mistakes and multiplication errors. So here, I don't have anything that's going to affect what's in parentheses, so I can just say x squared minus 4. And I don't have anything that's going to affect these parentheses either, so I can say 2x plus 1. And then I simplify this, and that'll give x squared plus 2x minus 3. Other notations we can have for this are f plus g of x, and that's how we would read it. F plus g of x. Or we'll say just f of x plus g of x. To emphasize the use of parentheses, let's go ahead and talk about g of x minus f of x. Again, each object gets substituted in just like we did before. X, that will be 2x plus 1 minus f of x, that's x squared minus 4. And now, because I have these parentheses here, that reminds me that the minus has to distribute over f of x. So we have 2x plus 1 minus x squared plus 4, and we can simplify that. We have minus x squared plus 2x plus 5. And we can say g minus f of x. Let's keep the same functions and talk about multiplication. We can say that as f of x times g of x, or as fg of x. These are equivalent notations. We assume that there's some multiplication going on right there. but we process the same as before. X squared minus 4 gets subbed in for f of x. 2x plus 1 gets subbed in for g of x. And then we go and distribute. So x squared minus 4 times 2x plus x squared minus 4 times 1. And then we multiply those out, so we get 2x cubed minus 8x plus x squared minus 4, and I can rearrange that to get 2x cubed plus x squared minus 8x minus 4. And there's our product. Just like with addition and subtraction, make sure that when you put your functions in, you have parentheses so you don't make sign mistakes or multiplication mistakes. But after that, everything happens just like it did in Algebra 1 and 2. You see these two guys together, you multiply them with the distributive law, or FOIL if you'd rather, and then you simplify, and that's all there is. Division is even super easier. That's not even a correct sentence, I apologize. Where I'm going to sub directly from f of x and g of x again. So x squared minus 4 divided by 2x plus 1. There's our function. I suppose in this case we could drop the parentheses if we really wanted to, but it's not entirely necessary. So those are the basic operations. Now the part that changes when we start talking about combining functions is the domain. Remember that domain is the set of x values you are allowed to use. That means you can't have any zeros in the denominator. If you have zeros in the denominator, that is not allowed to be in your domain. It also means you can't take a square root of negative numbers. So if your radicand is negative, that's not allowed. Now in chapter 4, we're going to add another one. We cannot take logarithms of non-positive numbers. That's another one that, but again, we don't have to worry about that one until chapter 4. So I believe, let me see if I still have it here, that we talked a little bit about domains of functions. Yes, we did. Right here, you'll recall this from your previous notes. F of x is 2x plus 8. Our domain was all real numbers because we have no division by 0, so x won't break a rule there. And we have no square roots, so we don't need to break a rule. We don't need to worry about breaking a rule there. And so my domain was all real numbers. Same thing over here. I have no division by 0 and I have no square roots, so I get all real numbers. But then down here, f of x is square root of x minus 1, and so this rule here had to be satisfied. I don't have any division, so I don't worry about that, but x minus 1 must be non-negative. It has to be 0 or positive, so x minus 1 has to be 0 or positive. Now again, look how I'm talking not about x, I'm talking about the entire radicand. Everything under the radical has to be 0 or larger. So I set this greater than or equal to 0, I solve it, and I get x is greater than or equal to 1, and that's what informs my domain. That's what informs my domain. Over here, I have x plus 1 in the denominator. I don't have a square root, so don't worry about that. But we do have division. So similar to the square root thing over here, I look at the entire denominator, and I set the entire denominator equal to 0. And anything that solves this equation, I'm not allowed to have. So here I say x plus 1 cannot be 0. If I subtract 1 from both sides, that means that x cannot be 1. So my domain, if we write it as a sentence, would be all x not equal to -1. And to write that as an interval, which is what I encourage you to do on this homework assignment, I have to take all the pieces smaller than -1, and that's this right here. I have to take all the x's larger than -1, but not including it, over here, and then I union them, and that is how we write this as an interval. So that's how we take domain. Just a quick refresher, how does that affect us here? Well, when combining functions, our new domain must satisfy both or all in the case that you're combining more than two functions. We have to satisfy both or all of the domain conditions. What does that mean? Well, let's do an example. Let f of x be square root of x plus 6, and let g of x be square root of x minus 3. So, what is the domain of f of x? Actually, just take a quick minute and find the domain of each function. Okay, what's the domain of square root of x plus 6? Anyway.
-7 to infinity.
-7 to infinity?
Yes.
Okay, if I put -7 in here though, what's going to happen? Remember, I want to solve x plus 6 is greater than or equal to 0. That is how we find the domain. We take the whole radicand, as in the entire radicand here, and I set it greater than or equal to 0. The reason we set it greater than or equal to 0 is we must have a non-negative radicand. We have to have a non-negative radicand. The radicand cannot be negative. So I have x plus 6 is greater than or equal to 0. What is the solution to x plus 6 is greater than or equal to 0? X is
0 to
greater than or
infinity.
equal to negative 6. So this is our domain. If I wanted to write it as an interval, well, look, I have equality. So we start with negative 6, and we just get larger from there. What's the domain of g of x? 3 to infinity, right? Again, we solve. X minus 3 is greater than or equal to 0, which gives us x is greater than or equal to 3. So the domain for g of x is 3 to infinity. So now let's look at some combinations. Let's just look at an easy combination. So we have f of x equals the square root of x plus 6. We have g of x equals the square root of x minus 3, and as we've just stated, the domain of f is negative 6 to infinity, and the domain of g is 3 to infinity. And now let's talk about f of x plus g of x. What's that equal to? Well, I have f of x, which is square root of x plus 6, plus g of x, which is square root of x minus 3. Just parenthetically, there's no like terms. So this specific problem is already simplified. We don't have to go any farther from here. But now we want to ask the question. What is the domain of f plus g? Well, the domain of f plus g, and we're going to state the definition here, is the set of all x values that are allowed in f of x and g of x simultaneously. That is, I can only use x values if they satisfy both functions. Well, what's the set of x values that does that? If I use negative 6, this guy's okay, right? He's fine. But if I use negative 6 over here, what happens? We end up taking the square root of a negative number, and that's not good. So it turns out negative 6, negative 5, negative 4, all the numbers in between, 0, 1, 2, I can't use any of them because they don't satisfy this function. It has to satisfy this one also at the same time. So that means this is the domain of f plus g. Because if I start from 3, this radical is taken care of, and this radical is obviously taken care of because 3 is bigger than negative 6. Another way to say this is if we look at the key word allowed in f of x and g of x simultaneously, then we see that the domain of f plus g is equal to the domain of f intersect the domain of g. It's the intersection of domains. Does that make sense? Okay, so let's do another transformation and see what else we can mess around with. Same f of x, same g of x. Oops, sorry. So they have the same domains. And now let's talk about f over g of x. Well, that means I take f, put them on the top. It means I take g, put it on the bottom. And what's going to be my domain? Well, from before, we see that the domain of f intersects the domain of g is going to be 3 negative infinity. It's going to be from 3 to infinity. But ask ourselves, is 3 allowed? Why not? Well, you can't shake your head no and not answer the follow-up question.
Because the bottom will equal 0.
Because the bottom will equal 0, and we cannot have that, right? If I take 3 and I plug it in here, 3 minus 3 is 0, and the square root of 0 is 0, but we can't have 0 in the denominator, and that would make it 0 in the denominator, right? If x equals 3, we have 0 in the denominator. So 3 is not allowed. So we have to rewrite our domain a little bit. So the domain is still going to go from 3 to infinity. The only thing that changes is that 3 becomes a boundary, not an actual value that we use. So I can get really, really, really close to 3, as close as you want. You just can't have it. So our lesson when dividing functions, eliminate any x value that creates 0 in the denominator. And we're going to add this to whatever we do with our domain. If we're dividing functions, we've got to take care of those zeros in the denominators. Now, there's one other thing that we need to talk about before we move on to finding domains of really weird functions. So the rules of domain are, and we've already talked about a couple of them. No zeros in the denominator, no square roots, of negatives. If you're dividing functions, check again for zeros in the denominator. In any combination, this is the other one, take the intersection of the domains. So this is what we've talked about so far, and actually, if we want to be correct about this, we want to switch the order, but they're all just rules. Okay, so what else do we need to talk about with domain? And it's very, very important. When combining functions, find the domain first. That is, before simplifying. You have to find it before simplifying. For example, if f of x equals 6 minus 1 over x, and g of x is equal to 1 over x, well, these domains are both really easy. The domain of f is all real numbers except for 0, and that's the same as the domain of g. So that's good. So what's f plus g? F plus g, well, I'm just going to take f, 6 plus 1 over x, plus g, minus 1 over x. There's my function, and I'm going to simplify it. Well, I have a negative 1 over x plus 1 over x, so that's equal to 6. Now you might be asked what the domain of such a function is. And you might be tempted to say, oh, well, 6 is a constant. That function never breaks. So it must be that the domain is all real numbers. And this would not be correct. The reason is, this has to be the domain. The domain is all real numbers except for 0. Why is that? This equality that I can take 1 over x and minus 1 over x and cancel them, this simplification holds only if we promise that x is never equal to 0. That's the only condition that I get to say that this right here equals 6, is because we keep the domain. So your domain has to be found first before you ever simplify anything. In fact, do we have time for that? Yes, we do. So we're going to get the calculator out here. Okay, so here's what we've done. I have 6 minus 1 over x plus 1 over x right here. And then I have 6. Now, if we graph these, all we see is this horizontal line right here. If I turn this function off though, and I go and turn the axes off, you should see it's small, but you should see a little gap there. You see that gap? That's 0. That's what we're not allowed to have. Let's make it a little more explicit. We'll go to the table. Yowzers, I don't want to start there. Table set, let's start at 0. And let's go by 1s. Oh, turn the other one back on. Notice that here I have 6s all the, whoops, sorry, here I have 6s all the way down, right? This is my y equals 6. Here though, when x equals 0, I have an error because the calculator knows that in this combination of functions, 0 is not in the domain. So these two only agree as long as I promise never to use 0. Does that make sense? You have to find your domain before you simplify. You have to find your domain before you simplify. Okay. So let's talk about some other functions. So let's find some domains of combinations. Let's take f of x equal to 1 over 4 over x minus 1 minus 2. And we already did a combination of radicals, so let's go ahead and do square root of x minus 2 over x minus 5. So here are these two functions. How do we find domains? Well, by our regular rules, x minus 1 is a denominator, so it cannot be 0. However, by the same rule, that cannot be 0 either. That cannot be 0 either, so I have to look at both. So, to talk about this one, I solve x minus 1. To talk about this one, I solve 4 over x minus 1 minus 2 equals 0. When I solve this, I'll get one of my excluded values, and when I solve this, I will get the other excluded value. Well, this guy's really hard, so I'll do that one. So, x can't be 1. Now this one right here might seem a little intimidating until you realize that this is just section 1, 2. That's all this is section 1, 2. So I can add 2 to both sides. So we get 4 over x minus 1 equals 2. Multiply both sides by the denominator. 1. Divide both sides by 2. And I get 2 equals x minus 1, or x equals 3. So these two values are excluded from the domain. So my domain is all real numbers except 1 and 3. All real numbers except 1 and 3. We would write that in interval notation as negative infinity to 1, 1 to 3, and 3 on ahead. You get 3 to infinity. Right? 1 is not allowed, 3 is not allowed. Now, to re-illustrate what we were just talking about, what if I took this and simplified it? What if I took this and subtracted the fractions and then took the reciprocal, because I got 1 over this. So what if I subtracted these fractions, got one fraction in the denominator, and then I took the reciprocal? What would the domain be? Your domain actually loses one of these excluded values. I get a value I wasn't able to use before. So that goes back to the rule we were saying before. Always find the domain first. Because this is algebraically equivalent to anything else only if we promise that I will exclude these two numbers. Does that make sense? Yes, no, maybe, perhaps. Only on Wednesdays. Okay.
Yes.
So how about g of x? Find the domain of g of x. Okay, so we start by finding the domain of each piece. What's the domain of square root of x minus 2? Two. Two to what?
X cannot equal 2.
X cannot equal 2? Why not? Let's see. If I do g of 2, that's the square root of 2 minus 2 over 2 minus 5.
Wrong!
0 over negative 3. Maybe we should try pushing the microphones and not using sign language. Just worry about the numerator right now. What's the domain of the numerator?
Would it be numbers?
All real numbers? So if I plug in 0 here, will that give me something we can work with?
All real numbers greater than 2?
Do I get to use 2? Do we get to use 2?
Yes.
Yes, we do. Okay. How about the denominator? What's the domain of the denominator? Well, do I get numbers smaller than 5? Why not?
Because you can't have a negative in the denominator.
Why not? Here's a negative in the denominator, and it worked out just fine. What can't we have in the denominator?
You
0.
can't have 0.
0. Everything else is legal. We just can't have 0. So what's the only number I can't have in the denominator?
5.
5. Every other number works. So negative infinity to 5, union that up with 5 to infinity. So we find the domain of each piece. Now we have to look at this as to what's going to work in everything. So can I use this part in my numerator? Well, not really. I mean, negative 10 is in here, right? So is 0. But that's going to break this right here. That's going to give me a negative in my radical. I don't want that. So, again, this goes back to taking the intersection. The intersection of 2 to infinity and the intersection of this, well, this guy has to be cut short, doesn't he? So I can't have all of it. I have to stop at 2. What about this part? Can I use all of this?
Yes.
Yes, we can. So that's the domain of g of x. I can use all real numbers bigger than 2, except for 5. So if we want that in a sentence, all real numbers larger than 2, except 5. Okay. Questions, comments, concerns, something that still doesn't make sense, anything like that? Now is the time. All right, last thing, we're going to talk about compositions and inverses. Compositions are easy. We're going to plug one function into another function. So let's take, for example, f of x equals x squared plus x minus 1. And we'll take g of x equal to 2x plus 3. So the notation for composition goes like so. We read it as f of g of x. Yes, that's a lot of ofs. This is synonymous, though, with the following. I'm going to take g of x and I'm going to plug it into f of x. So what does that mean in this case? It means that everywhere I see an x in my f, I'm going to plug g of x into that. So that means I have g of x squared plus g of x minus 1. that this right here is literally what composition means. Now, this isn't very useful to us, so we're actually going to take the 2x plus 3 and put it in there. So that gives us 2x plus 3 squared plus 2x plus 3 minus 1. And that's what it gives us. And then what's the domain? Well, the domain is going to be, we have all real numbers here, all real numbers here, so the intersection will be all real numbers. So we don't have to worry about it. Make sense? We literally took this and plugged it into the x values here. If I went the other way, so I switch the g and the f, that means I'm going to plug f of x in everywhere that we have a g, or everywhere that we have an x in g. So that's 2 times f of x plus 3, and we already know what f of x is, so that's 2 times x squared plus x minus 1 plus 3. And we can simplify this and we will find joy. If you wanted to evaluate this at a point, again, same f, same g, but if I wanted to say f of g of -1, we have 2 options. Option 1, we compose the functions and then plug in. So that said, if we go back over here, we have that composition. So it says 2x plus 3 squared plus 2x plus 3 minus 1. And now I'm going to plug in minus 1. And so that's 2 times minus 1 plus 3 squared plus 2 times minus 1 plus 3 minus 1. And we calculate. That's what? -2 plus 3 is 1 squared plus 1 minus 1, which is equal to 1. Option 2, we find g of -1. That's step 1. Step 2, we plug the result into f. So what's g of -1? That's 2 times -1 plus 3, which is 1. So then this goes into f of x. And so that's 1 squared plus 1 minus 1, which is the same thing that we had over here, which is equal to 1. They're the same. Do whatever makes you feel warm and fuzzy. Personally, I prefer doing this. I prefer option 1 because I know then that I've done this, and I can, if I need to do it for another value really quickly, I can. So the algebra work is already done. But if this makes you feel better, use this. It does not matter. Make sense? We take one function, we shove it inside the other. Now, the dirty little secret that we haven't told you is that you've already done this. Back at the very beginning of chapter 2 when we talked about the difference quotient, well, what's that? F of x plus h minus f of x divided by h. Well, this right here was a composition. And this right here is subtracting functions. And this right here is dividing functions. So a lot of this stuff you've already done. We just needed to make it a more general case so that we could talk about domain. That's the punchline to what we've spent essentially 4/5 of class on, is this right here. The other one, transformations. A times f of x plus c plus d. And again, right there, we have composition. And then we multiplied functions, and then we added functions. So transformations are also indicative of what we're talking about today. We've already done them before. We just want to talk about them in a more general case. All right, last thing. We got 10 minutes. We can do it. Yes, we can. Is inverses. Not every function has an inverse, but the ones that do are kind of important. Right? This is what we know about functions. It takes some value x to some point in the range f of x. What I want to know is, do I have a function that takes the y value back to x? If there is, that's called the inverse. So we have one test. We have a requirement, rather. F must be what we call 1-to-1. That means 1x goes to 1y. That's basic, that's the function rule. And 1y only has 1x. This is best described by what we call the horizontal line test. That is, a horizontal line touches the graph only once implies 1-to-1. Let's see how it works.
Can you put your paper back?
Oh, sorry. So what we want to be able to do is look at the graph, and if the horizontal line touches the graph only once everywhere, then it's 1-to-1, and I have an inverse. If it doesn't, then I'm going to have to do something about that. Ready? Sorry, I didn't
Yes.
mean to rip it so fast that time. Okay, so let's take the square root of x plus 3. There's a function. Oops, sorry. If I draw horizontal lines, I only touch the graph once each time. So x square root of x plus 3 is 1 to 1. It has an inverse. On the other hand, let's just take the basic x squared function. If I draw a horizontal line, that is not 1 to 1. So there's no inverse unless I do something special. And that special thing is called restricting the domain. I can only take a 1-to-1 portion of it. So we can keep the positive x values. That's a restriction. We can keep the negative x values. That's a restriction. Right? This is 1-to-1. This is not. This is 1-to-1. This is not. So if I restrict my domain, then I'm allowed to have an inverse. How do we find an inverse? Step 1, let y equals f of x. Step 2, switch x and y. Step 3, solve for y. So, for example, well, let's take f of x equals the square root of x plus 3. That's the one that we had earlier. So, step 1, I'm going to let f of x be y. So now I have y equals x plus 3. Step 2, I'm going to switch my x's and y's. That literally means just change their places. So I'm going to say x equals the square root of y plus 3. Step 3, solve for y. So the first thing I can do is square both sides. The next thing I can do is subtract 3. And this is my inverse function. Make sense? Okay, real quickly, because we only have about 3 more minutes, how do you know if it's an inverse? How do we check our work? We check inverses by composition. That is to say that f of f inverse of x has to equal x. And if I do it the other way, I have to get that. So let's do one way from our previous example. So we've got f of x, that's square root of x plus 3. We have f inverse, that's x squared minus 3. And now I'm going to compose them. So f of f inverse of x, that means I take f inverse and I plug it into f. So that will be the square root of x squared minus 3 plus 3, right? Well, I can drop the parentheses. It shouldn't be too hard to see that these 3's will go away. So there's my square root of x squared. But what's the square root of x squared? It's x. So what does this mean? This means that for any x value that I plug into the inverse function, the original function undoes it and takes me back where I started. Same with the other way. Whatever I plug into f inverse undoes that and takes me back to x. That's how you check that you have an inverse. Make sense? Yes, no, maybe? Okay. Homework stuff, please, I cannot emphasize strongly enough, make sure you start it today. Email me any questions you have so that you can get on top of that and be ready for the exam on Thursday. That said, again, make sure that you're ready for the exam, make sure you're doing the homework. If you're not on My Math Lab permanently yet, you only have today and tomorrow to do that, so please make sure that your My Math Lab access is permanent access. I don't want you getting caught with no homework access after the first exam. So make sure you're doing that. And again, if you've got any questions, email me and let me know, and I'll see you guys for the test on Thursday. Have a great day, everybody. See you later.